Audio Jungle. Audio Jungle.
Alright, so in torsion, till now we had seen all the arrangement, series and parallel, and for that we had seen the formula also. Okay, that torque relation and that angle of twist, that relation for the series and parallel we had seen in previous lecture, right? Now we'll talk about the Bread-Batho theory, and basically this Bread-Batho theory is what for given for the closed section, thin wall closed section. So Bread-Batho theory. Now this is the important topic for the gate aerospace. Why it is important? Simple, because thin section or you can say plane stress, if you heard, then that plane stress means that thickness you are considering for the section or perpendicular to plane, that thickness you are considering, it is negligible. Okay, so it is the consideration of the thin section. So that is also very important, because in aircraft, whatever the structure we have to go for the consideration of thin section. And similarly here, if you have a twisting moment in that section and we are considering it is thin section, so what will be the calculation for the torsion, where will be the shear, more shear stress, what will be the shear flow for that, how to get the calculation of the torque for that particular section. So that all those things we have to do here. So the bread-bath theory, which is given for thin wall closed section, thin walled closed section. Okay, and especially the whole analysis, it was given for the torsion. Okay, the whole analysis by this theorem is what? For the torsion of this thin wall closed section. Okay, that is also the reason why it is important. So we have approximation of thin wall section. So what is the approximation of thin wall section? Of thin wall section. So the thin wall nature of aircraft structure to make simplifying assumption in the determination of stresses and deflection produced by the bending. Thus, the thickness T of thin wall section is assumed to be small compared with the near cross section dimensions. That means if you are talking about the diameter for any tube or for any vessel, so compared to diameter, that thickness of that section will be negligible, or it is assumed to be a small compared to their cross section. So that cross section can be anything. If it is circular, then you talk about diameter. If it is rectangle, then you talk about the length and width. Okay. So compared to other dimension, if thickness is what is small, so that section will be considered as a thin wall section. Okay, or that tube will be considered as a thin wall tube. So that's the reason for this cross section, the stresses may be regarded as being constant across the thickness. Okay, and if it is thin wall section, so whatever the higher order or higher power for the thickness will come into picture for in calculation and all, then that portion you can truncate. Okay, so I mean that portion you can make it zero. Like just for example, if you have, suppose, see, this is one rectangle cross section. Okay, and this rectangle cross section, this is what thickness, like this. Okay, now this is nothing but, you just say B. Okay, this is the B. And if you talk about the thickness here, thickness, it is nothing but T. This thickness is nothing but T. You say this length is nothing but L. So for this particular plate, where the length is L, width is B, and thickness is T. Thickness is T. So if you check this thickness will be very, very lesser than length and width both. So this section will be considered as a thin cross section, or this section, or this like tube. Suppose this is the square, but similarly if we have a tube also, suppose this is the tube, check, or any circular cross section. So here this diameter is what, capital T, but if at the same time if you talk about the thickness, this T, so compared to this diameter, this thickness is very, very small. Then this will be considered as a thin cross section or thin wall section. So in approximation, what is the approximation? The approximation is thickness okay, thickness, or you can say the higher power of thickness, higher power of thickness will be neglected or truncated. Truncated in calculation. So what is the mean of it? That meaning is what? Higher order. So higher order in the sense, it is T square, so make it equal to 0. It is T cube, make it equal to 0. Okay, similarly any higher order, T to power 4, make it equal to 0. T to power 5, make it equal to 0 somewhere.
Sir,
Yes.
is a small value then?
Thickness is a small value. That's only I'm saying. Compared to another dimension like length or width or diameter, if
Yes, sir.
thickness is very small. Okay.
Oh, okay.
If thickness is very small, then in calculation, suppose you are calculating moment of inertia, or if it is circular cross sections, you are calculating the polar moment of inertia. So that time, anywhere if you are getting T to power 2 or T to power 3 or T to power 4, then that value you can consider as a 0. I mean that section, suppose BDQ by 12, that formula you are getting BDQ by 12.
Yes.
Okay.
Yes, sir.
So that part will be 0. Hope you understood this.
Yes, sir. Understood.
Right. Now, so just for before going to this Bread-Batho theory, approximation of thin wall section, hope you understood. Now, just for example, we'll consider the thin section, and we'll take this I section here. So this I section, or you can say C section, you can take any section. Suppose this is the C section. Okay. C section, and this is the thin section. Okay. I am talking about thin section. So now this is the C channel. It is called C channel. C channel. For this, you will get the idea what is the meaning of this approximation. So suppose this is the x-axis. So obviously here this C channel, it is symmetric about x-axis. I am considering this width is nothing but b. So obviously this will also be, because it's a symmetric. This whole length is nothing but h, or you can say 2h. So this will be h, and here also it will be h. So you consider whole length is what? 2h. Alright. Now for the thin section C channel, suppose we are interested to calculate Ixx, and at the same time for this section that thickness is nothing but it is T. Everywhere this thickness is nothing but T. Listen carefully because it's very important, okay? And everywhere the thickness of this channel is nothing but T. Thickness is T for this C channel, and width is B, height is 2h. Now if you calculate Ixx for this, so how many sections we have? Section 1, this is section 2, full length I am talking, and this is section 3. So we have Ixx 1, Ixx 2, Ixx 3. Now if you check the both Ixx 1 and Ixx 3, this is what symmetric, so you can write 2 times of Ixx 1 plus Ixx 2. That meaning will be same. Okay. Now if you talk about what is the value of this, any we can start Ixx 1. So 2 times Ixx 1. What will be the Ixx 1? This first section is nothing but you just say this is what A, this is what B, this is C and D. We are talking about AB. So what is the thickness? It is T. What is the width? It is B. So what is the moment of inertia about CG? It is BTQ by 12. Because thickness is T, hence it is BTQ by 12. If this thickness is D, then BTQ by 12, that you know. Plus, because we are talking about the moment of inertia about this x-axis here, this is the x-axis, and obviously CG will lie on this x-axis because it is symmetric. Okay, about x-axis. So somewhere CG will lie here, okay, on this axis. Now if you take moment of inertia from this about this x-axis, so you have to apply the parallel axis theorem. So this length you should know, this length is given h. So what is the formula? AY square, that parallel axis theorem, AY square. So A is the area. What is the area? It is B into T. It is area into AY square. So Y is the CG distance from the axis. So you are talking about the moment of inertia about this x-axis. Hence that distance of the CG from this x-axis to this AB section, and it is nothing but exactly h. Or also you can say it is h, you can say it is h, and this thickness is T. So again this T by 2 you can say, because you can consider this is the thickness T. So if you take this section separately, so you may get like this. So this is nothing but T. So where CG will lie, it is T by 2. Again it will go for the another division in T you may get. So that will be the value of you can say h plus T by 2. That will be the y distance. But I am considering, okay, this thickness T, it is very thin, so this h length I am taking. So it is B is the B into T is the area into CG distance. So CG distance I am considering h. So it is h square. So it is what? ICG, that is the moment of inertia about CG for this AB section, plus AY square, that is the perpendicular axis theorem. This is for what? Same. I mean Ixx1 and Ixx3. It will be same. So that's the reason I have 2 times here.
Sir, h square.
Sorry.
Sir, h square. Sir, this h square I didn't understand.
Okay, that if you remind that parallel axis theorems, it was what? It was the taking moment
CG
about
distance. Yes, sir.
is equal to ICG plus AY square.
Yes, sir. Y square.
So y square is the distance from CG about which axis you are taking moment. So we are taking moment of inertia about this x-axis. So this x-axis distance from this distance, this axis distance to the section distance. What is the section AB? So what is the distance in between? It is h. That's the reason it is instead of y, it becomes h.
Okay. Okay, sir. Okay, sir.
Right. So this is what two section you have taken. It is 1 and 3.
3, yes.
Yes. And now for middle one, if you check, it is nothing but thickness is what t, and what is the length for this? It is h. So it will be th cube divided by 12. So th cube by 12. Okay.
The whole length is
Whole length
2.
is 2. Sorry, it is h plus s. It is 2. Make it correct. It is
2h cube.
yes. It is t times 2h cube. Now this is fine. Okay, so this is the I-axis. So now because we are talking about the thin section, so what is the approximation I have given? That approximation is what? Any higher order term you have to neglect. That is the approximation of thin wall. Alright. Now if you check where is the higher order? I mean if you check t cube, it is higher order, so simply you can make it 0. That is the approximation. So what will be the moment of inertia for this C channel? It is nothing but 2 times of bt h square. So you can write 2 times of b t h square plus this t times of 2h cube by 12. So this is what moment of inertia for the thin section. So similarly for any I section, T section, L section, what we had seen in our first or second lecture, that moment of inertia for different section, if the approximation is for the thin wall or thin section, if you have, you can say it is thin I section, thin T section, thin L section, this is the thin C channel. So for any thin section approximation you are taking, then the higher order of thickness will become 0. So for example, I have shown you, and again one more reason why I have taken this, because for the C channel, that shear center they have asked many times. So definitely moment of inertia required. So this moment of inertia you should remember for the C channel. Hope this one is clear to you. Now, moving ahead, so this approximation, hope you understood. Now, assumption for this, okay? So, for grid battery, we have assumption. What are the assumptions? You need to remember, the assumptions are there is no tangential normal stress, so you can say hoop stress will be 0. The shear stress perpendicular to the longitudinal axis, that also be a 0. So these are the assumption here we are going to take. So shear stress perpendicular to longitudinal axis are neglected. Number 2, hoof stresses are 0 for that section, are 0. And third is very important, the tube ends and cross section are free to wrap. That means there is no normal stress. Okay, that meaning itself is there is no longitudinal normal stress. All right, and the last one is the cross section thickness may vary along along the circumference. But constant along longitudinal axis. So this is given for the thin wall closed section. This is given for thin wall closed section. So now if you are talking about the thin wall closed section, so you may have the diagram for the thin wall closed section. It is like C. Oh, sorry. It may be like this only. So these are the assumptions. Based on this assumption, we have to discuss. Okay. So we have a, this is what inner boundary, and this is what outer boundary. The thickness here it is nothing but T. This is the thickness. Anywhere if you say this is the one section, so here if you check, so we have a shear stress. Okay, the inner and outer boundaries are nearly parallel. Okay, so resultant shear stress through out wall are tangent to the medial line. So how to get this medial line? It will be in between to the inner and outer boundary. So this will be the median line. Check. This is very important here, and they are asking question based on this in gate. Okay. So this is called, sorry, in between. So this is called median line. What it is called? It's a median line. So whatever the shear stress you may have, shear stress, resultant shear stress throughout wall are tangent to the medial line. That you need to remember. Okay. So this is the one cross section you have taken from the tube, or you can say any arbitrary vessel section. It is not like compulsory. It should be circular. Assumption you have seen that tau resultant is approximately constant through the thickness T. Okay. So now this is the 4 point. Now tau resultant, fifth point is tau resultant tau resultant, which is the shear stress, is approximately constant through the thickness T, and the resultant, this you can say this tau resultant shear stress through wall R tangent to the median line. This point is very important, okay? Where this line LINE, where this tau resultant will be acting, it will be acting tangent to the medial line. Where you will have a median line, it will be inner and outer boundary. In between one dotted line you are getting here, this is called median line. Okay, so for this reason also you may say that whatever the area, inner area, I can say, because it is thin, so inner area will be equal to area of outer, and this area will be constant. This area will be constant. Okay. Sorry. This area will be constant. Fine. This is the one thing you need to remember. Now you will talk about the if there is a torque acting on thin closed cross section, or any, or you can say it's a representation of forces on thin closed cross section under torsion. So what will be the conclusion you will have? Okay, that is also one analysis we need to do here. So now this is called representation of forces on thin closed cross section under torsion. What we will do, we will have this arbitrary shape here. Check this arbitrary shape you have. Even if you want to draw here, you can draw. So all right, arbitrary cross section. Where is the median line? This is the median line. Okay. Now you are having the axis, you can say this is nothing but y-axis and this is x-axis. It's your choice. You are talking about the coordinate systems. Any coordinate you can take. It's not a big issue. Now you can take that one section, okay, and this section is nothing but, at this section you are saying the force is what acting. Where is the section? The section is, you are talking here. Okay, and this is nothing but distance h, okay, and here this is the one section. You are saying this thickness is nothing but ds. Over this section the force is acting tangent to the medial line, and this force is nothing but the shear force, okay. Here you know the thickness is what t, and in fact here the torque is what acting t because of the force, shear force, definitely torque you may have. So the torque is what acting like this, okay. So what will happen? So what is the shear force? It is shear stress into area. So ds is the area, or you can say elemental length, and ds into 1 will be the area, okay. ds into 1 will be the area. So, and shear stress in previous also you had shown here. See, this is the shear stress acting tangent to the medial line. See that resultant shear stress, it is tangent to the medial line here, okay. So you can say it is tau into shear stress into area, okay. So if you check this ds length, okay, now one you can start from the taking unit area, unit thickness. Other you are considering this is thin section, but t it is suppose given, like here it is t is mentioned, so this area will be ds into t. So area is nothing but ds into t. That is the ds is the elemental length, t is the thickness somewhere, and here shear force is what acting because of the shear stress is there. So shear stress into area will give the shear force, okay. This is what shear stress. This is what elemental length. This is what thickness, okay. Now, so this section, even if you want separate you can take, okay, separate you can take somewhere. So you can consider this section, and you can say here the shear force which is we can say here we have a shear flow, and from the origin this is nothing but you can say this length is nothing but h. In fact, actually the perpendicular distance you should write here, so you just make this length, you say, because now perpendicular it seems like here, so better you just make this is the h length, okay, so that there should not be any confusion. This is the h. So if you check what is the triangle, so triangle is nothing but base into length. So this length what you have, it is the ds length, okay. So triangle you have o AB. So triangle area is nothing but 1 by 2 base into height is h. Okay, this is nothing but because the ds elemental area elemental length, so this area will be elemental area and it is nothing but ds into h divided by 2. This one you need to remember. All right, here if you check the shear force, so this shear force is nothing but F this value is nothing but tau ds into t. So you may get this. Where is the shear force acting? Here, tangent to the medial line. Where is the tangent? Medial line. You have drawn this single line, so this is the medial line. Okay. See, this medial line is nothing but this dotted line. So now this dotted line only I have drawn. So this is the medial line, and here we are showing this shear force is what acting tangent to the medial line. Okay, tangent to the medial line. So what will be the torque? Torque T is nothing but the shear force into perpendicular distance. What is the perpendicular distance? H. H is the perpendicular distance. Shear force into perpendicular distance. So this torque is equal to F. F is nothing but tau ds into T into H. Now from here check what is the H. H is nothing but 2 times of dA divided by ds is the H. So tau ds into T into H is nothing but 2 dA divided by ds. So ds cancel out. T is equal to tau into 2 times tau into T into dA. So T is equal to 2 times, you can say this value, which is nothing but, and obviously this is the elemental value, so this torque will be dt better. So there should not be any confusion, otherwise you may think like this elemental area you are getting, so how this is the full torque. So this is the elemental torque basically dt. So 2 times of the tau into T into this area dA. Okay. So what about this tau into T? What about this tau into T? That is the important point. How to get this tau into T? So this tau into T is nothing but called a shear flow. What it is called? Shear flow. So whatever the diagram we have, in the same diagram we have to check this section. We can say we can take one wall section. Here it is nothing but like this. It will be more clear to you. Okay. Now if you check that this is the infinitesimal piece of wall, whatever the wall you have here, any section you can cut, so you will get this like this. So now if you check the shear flow analysis, you just say this section, this point is nothing but somewhere here you can take, no? Here only you can mention somewhere. Suppose this section you are talking, this is what A and this is what B. So for this you are going to take this section separately, and this is what A and this is what B. So obviously this will be the B dash and this will be the A dash. Now so we will have a, we'll take the moment, we can take the axis. So we have basically xy plane. If you check here, this was the xy plane, this is the x and this is the y. So where will be the z? So z will be just perpendicular to this, yes or no, perpendicular to this, or perpendicular in vertical direction we can show, because this is the xy plane. So obviously perpendicular z means perpendicular to the plane it will come. Okay, so now you can check, this is what z and this is what y, and separately you can take this is what x and this is what y. So about z you have to take the force balancing. So I can say this perpendicular to xy plane, this length will be what, dz. Now if you talk about the shear stress, so definitely shear flow will be like this. So here you just say that thickness is what, because this is in A, so thickness is what, just say TA, and shear stress you say because it is in A, so it is tau A. Similarly, here also you can say that thickness is what TB, and shear stress at this point it is tau B. Okay. So now if you write the summation of force in z direction and make it equal to 0 in perpendicular to the xy plane, perpendicular to the xy plane, if you take this, then what value you will get? So what is the force? It is stress into area. So in z direction, that stress tau into area will be thickness into distance. What is the distance? It is dz. Okay, so it is nothing but, if you calculate this value, so because it is, this thickness is what like this, but if you check, it will be like this, yes or no? Okay, so this is nothing but thickness tau a. So tau a, sorry, ta thickness, and dz is the perpendicular distance. So ta into dz will be the area, and what will be the stress? It is tau a at this end. So in vertical direction, because it is going downward, so it is nothing but tau a stress into area. Area is nothing but ta into dz. Here, because it is, this flow is what going downside, so here it will go upside. So I mean it will make a path, closed path here, because it's a closed vessel, closed tube. So at this end you are talking only A and B section. So at this in B, see, this stress direction is what, positive, so it is tau B into area. What will be the area? Thickness into, thickness is nothing but you can say TB into the stress, sorry, into the distance dz. So this will be the area, and this is equal to what? 0. Summation of force in vertical direction, it is 0. What is the conclusion you are getting? dz dz both side you are getting. So here you are having tau a into ta plus tau b into tb equal to 0. That means tau a ta is equal to tau b into tb. So this was the AB section. Okay, and you can say like, okay, how this section is coming? So actually this is the cross section we are having. Maybe this section is what, like this. Okay, so now you had taken only A and B, so definitely thickness in z direction it will have, this thickness will be have. So this thickness, sorry, depth is, you have z direction, so that z direction you are getting here, this one. So this was AB section we had taken. Similarly we can take anywhere this CD section also you can take C and D, and for this also you can analyze. Okay, anywhere. So if you do for the CD also, so what value you will get if you talk about the CD? So for CD section, so you will have a stress at C into thickness at C is equal to stress at D into thickness at D. So this value will be same. So that what is the mean of it? This is for the AB section. This is for the AB section. So what is the mean of it? Meaning is very simple. Any section you can take tau C T C is equal to tau D T D, and so if you check this, what is the overall conclusion? The shear stress into thickness, this will be what? Constant. This product will be what? Constant. That's the mean of it. The product will be constant. Okay. So this product will be constant, I must say. This product must be constant. So if you deal any cell or any closed contour, so you will have this uh, like product of shear stress and thickness. For that section, this product will be constant. So this constant parameter tau into T, tau into T, I mean shear stress into thickness, this will be a constant parameter, and this constant parameter is called as shear flow. This is very important. It is noted by capital Q. Shear flow. Capital Q. This is what? Shear stress in that particular section. Suppose it is AB section, and this is what the thickness in that particular section. So thickness of the vessel, and this we are talking about the closed vessel. Okay. So this, if you are going for this particular case, so it is just like, if you remember analogy, if you check what is the analogy for this analogy, you have 1D pipe flow. What was the 1D pipe flow? If you remember, here the velocity was V and this area was A. This area was A. So what was the discharge? It was area into velocity, and it was constant. Discharge was constant, yes or no? So this was discharge, this was area, this was velocity. So you said like, okay, discharge throughout the pipe will be constant. So similarly, this is what shear flow, and this shear flow will be constant throughout the section. This is valid for closed section. This is valid for closed section. This is also valid for closed section. So this, all the analysis what you have seen, it is for the thin closed wall or thin closed section or thin closed tube. Okay. Hope this one is clear to you. Now coming to this analysis, tau into T is called shear flow, and it is noted by capital Q. Now what was the dt? So this dt, now torque, check torque. Here you had calculated dt, that value if you check, it was 2 times tau into T into dA. 2 times tau into T into dA. So 2, this tau into T is nothing but Q into dA. This is what dt. If you check the total torque, so what will be the total torque value? The total torque is nothing but it is the T. So for the whole section you have to integrate. Now instead of this dA, I mean take this small elemental area, integrate this, then what you will get? 2, this A full capital area you will get, and this is the shear flow. So what is this A? This A is nothing but this whole cross section area. A is the whole cross section area. What is ds into T? This is the elemental area which is called dA. So if you integrate this full, then you will have this you can say whole cross section area. Okay, so I hope this one is clear to everybody. Now if you say, like, again, if you have doubt for this, like this analysis how it comes, so you can draw this diagram. By this diagram also you can understand, it's a simple only. You have taken this portion. Okay, this was the ds elemental length. Your that tangential force was acting here, or acting along the tangent to the, you can say tangent to the meridian line. So you can say this tau is shear stress, and this is the force which is nothing but shear stress into ds into T, shear stress into area. And if you write the torque, so perpendicular distance you need to take. This is nothing but h, what you have taken here. The same diagram I am drawing here. This is the ds portion for this. If you write the torque about this point O, so it is nothing but shear force into perpendiculars that you have done here. Okay. All right. So there should not be any confusion. And what area you are taking? This is the area. If you say ds into T, so this is nothing but dA, and this area is nothing but dA. What is this area actually? So this area, always remember, it is the closed vessel area. Okay, closed section area you can say. This area is nothing but closed section area. There should not have any confusion. This area always will be the cell area or closed shell area. Better I will write here, otherwise sometimes missed. Closed cell area. This is called closed cell area. Okay. Now finally that result you got. So T is equal to 2AQ. This result is nothing but was a weighting result, and this is called as Bredt-Bateau formula. What it is called? Bredt, B-R-E-D-T, Bredt-Bateau formula. It is very important, very, very important. If you check the conclusion here, what is the conclusion? The conclusion is torque is for any closed cell, for closed cell. Now for single marks question, just listen. For the closed cell, torque is directly proportional to shear flow. That means Q. Torque is also directly proportional to cell area. Torque is also directly proportional to cell area, which is nothing but A. That cell area can be anything. Okay. So these 2 points you need to remember, point 1 and point 2. What about the shear flow conclusion you got? Shear flow you have seen here, it is nothing but Q. What is the Q? Tau into T. So if you check this shear flow, it is also if you check the unit, this is stress is nothing but Newton per mm square or meter square, and this thickness is what mm, you can say. So what is this? This is nothing but Newton per mm. So this shear flow also, you can say it is nothing but the unit of shear flow. If you check, it is nothing but shear force per unit length. Okay, shear force per unit length. Shear force per unit length. Okay, that is nothing but Newton per mm. That also you need to remember. Shear force per unit, and this is what constant. This is constant for the along the section. Okay, all right. So this analysis, what you have seen, it was Brett-Bateau theory, and it was very important for your for your gate, as well as for the one day exam. If you go, then you may have this type of analysis. Okay, now if you talk about the what is the shear stress, what is the shear stress in case of the closed vessel or closed tube. So this is nothing but shear stress. If you say this is the shear flow, and we'll talk about the shear stress. So shear stress is nothing but tau. Check what is the formula you got. You got T is equal to 2aq, and q is nothing but tau into T. So from here, if you check, that stress is nothing but torque divided by stress is nothing but torque divided by 2 times of area into thickness. Let me write this. Here stress is nothing but torque divided by 2 times area into thickness. So this is also very important formulation. Okay, all the formulation are very important, and how it looks like. See, this is what the thin closed section. Just say this is the thin closed section. Okay, so this whole shaded portion will be the area. This is nothing but area. For this section, thickness will be given to you T. And if you want to calculate what is the shear stress acting over this, so definitely this is suppose rectangular shaft or rectangular beam or rectangular tube you have. So this torque is what T. If you want to calculate shear stress, then this will be the formula. So area will be the shaded area or closed cell area. That you need to remember. Okay, that you need to remember. So this is the problem. Now if we go for the problem calculation here. So now see, we have problem number 1. Check. Suppose question is a tube two mm. Okay, a tube 2 mm thick has the shape shown in figure. Find shearing stress caused by a torque of 600 Newton meter. 600 Newton meter. So check figure as shown in figure. So this is the figure for the problems.
Sir, what is the torque value? 600 Newton meter?
Yes.
Okay, sir.
All right. So this is the vessel. For this vessel, you need to calculate the shearing stress, and obviously the shearing stress you are getting because of the applied torque. Applied torque value they have given to us. This is what semicircle, and this semicircle value they have given to us. Just say this is the median line in between. So from the median line, this value they have given to us. This is 10 mm. 10 mm. 10 mm. Okay. All right. So how to get the problems? It's very simple only. If you check, if you want to calculate the area, so obviously that area will be what? See, so say A, B, C, D, and P and Q. So A, P, D and B, Q, C, it is semicircle. So if you calculate the closed cell area, so you have to mark that. So this marks always you have to you have to draw the hash line from this median line. Okay. So if you do this, then this will be the area. Okay. And this area, I think it is added that radius was 10 mm. Okay, you check the diagram. So this shaded area we want. This shaded area is nothing but this one. Semicircle is here and semicircle is here. Okay, semicircle, both side. All right. Both side, and radius is what, 10 mm. So it may be that diagram is what, not symmetric both side, but it's 10 mm both side. So what will be the area? So area will be pi r square by 2. Pi r square is the area of the full circle, but both side it is half half, so it is pi r square by 2 plus rectangle area. So this rectangle area, if you check, this is the radius. So what will be the diameter for this? So diameter will be, I think, 20 mm. 10 plus 10. So 20 mm. This is what, 80. This is what, 20. So it is 80 into 20. Yes, if you calculate this area, so it is pi r square by 2, pi r square by 2, it is pi r square. So I can say pi into r is nothing but 10 mm. So plus 80 into 20. So this area, if I get this, so 16 plus 1600, right? Plus pi 10 square, 100, pi is 3.14, is approximate. Point m square. This is the area. So, so please, this you need to remember. This is the hash. Hash means this portion you need to take outside for the calculation. Now your problem is what, solve using Brett-Bateau theorem, T is equal to what? 2aq, or you can write 2a tau into thickness. So what is the tau? It is torque divided by 2a into t. If you check the torque you have 600 Newton meter, but area you have in mm square, and thickness is also in mm, 2 mm. So better you convert this 600 Newton meter into millimeter. So 600 Newton into millimeter, so it is 10 to the power 3. Now it's Newton millimeter. 2 into area you have calculated here, it's 1914, into thickness it is 2 mm. 2 mm thickness you have, 2 mm. If you calculate this stress, so how much you may get? You may have, where is my calculator? So approximate it is 78.36. All you have converted into millimeters, so it is Newton per mm square. And you know very well this value also you can write in megapascal. It will be megapascal. This Newton per mm square, you know, this conversion of the unit, this is also a megapascal, because mega is what, 10 to the power 6, Pascal is what, Newton per meter square. So here we have Newton per mm square. If you convert it, 10 to the power 6, 10 to the power 6 will be cancelled out. So ultimately this megapascal will be Newton per mm square. Always remember, okay? Don't get confused. Anyway, so all right, so this is the answer. Fine. So this type of question for one day exam, very frequent, they are asking from the Brett-Bateau theory. Okay. Like one more question we have. This is problem number 2. Now we have a tube. Next question we have, it is a tube of 2 mm thick, has an elliptical shape. As shown in figure. What torque will cause a shearing stress of it is 78.36. It is shearing of 78.36 megapascal. So see the diagram what they have given to us. It is elliptical. Okay. So for this ellipse, they have given all the dimension. What are the dimension? Dimension they have given to us. It's nothing but thickness is 2 mm. Major axis, I mean this length they have given us. Okay, so wait, this length what they have given to us, it is from the median line. Where is the median line? Median line will be here only. So this very important point I'm marking every time, so it means you need to remember. Okay, from the median line, this distance they have given to us. How much? It is nothing but, you just say 20 mm, and this side is given 10 mm. So solution of this problem is simple only. What will be the solution? You know what we need to calculate. They are asking what torque. So by using Brett-Bathe theory, Brett-Bathe theorem or theory. Okay, what it is? It is T is equal to 2AQ. 2AQ is nothing but tau into T. Now if you check, we should know the formula now, the ellipse area. What is the ellipse area formula? It is 2. Ellipse area is nothing but pi into AB into tau into thickness. A is the, if you remember, that dimension major axis and minor axis. Okay, so here area of the ellipse,
Pi AB, yes sir, okay.
pi AB is the area of ellipse, remember it.
Okay sir.
Let me write area of ellipse, area of ellipse. Okay, now so what is this? A is the major axis, and it is not only A, it is 2A. You heard semi-major axis, semi-minor axis. So A is the semi-major axis. Semi means this portion. This is what A, and this is also A. You recall that ellipse. So,
Yes sir, this is in space dynamics.
Yes. And this is what semi-minor axis B, semi-minor axis. So this total length is nothing but 2B. Okay, always remember. So what is the A here? If you check, A is 10 mm. What is B here? It is 5 mm. Now we will use this formula now. So torque is nothing but, see, it is 2 times pi. A is nothing but 10 and B is nothing but, I think, 5. B is nothing but 5. Into tau they have given to us, it is searing stress 78.36. 78.36, it is megapascal or it is Newton per mm square. As I told you, it is same. You should know that conversion. And then thickness is given 2 mm. Check, this value is 10 and
Okay,
this,
sir,
this
5,
value
yes.
is 5. It's a 49210
0, yes.
Newton mm.
Yes sir.
This will be the torque. So I hope this one is very clear to everyone. So now just we have seen the thin cross section analysis and approximation for thin cross section. So we'll write the polar moment of inertia, okay, for different thin wall, open thin wall and closed thin wall. So Brett-Bathe theory is what work for the closed thin wall, always remember. Okay, it is only for the closed thin wall or closed thin tube or closed thin any arbitrary section or circular section, you can say. Now, so we'll write the thin wall, which is nothing but two types of the thin wall section we have for the analysis. It is nothing but, and both type of question they are asking in exam. Okay, so first is the closed thin wall or